Discontinuity versus differentiability. In the previous unit on limits, we discussed what must be true for a function to be continuous. The definition of continuity states that a function value at any constant c exists, the limit as x approaches c of f of x exists, and the limit as x approaches c of f of x is equal to the function value at c. And the differentiability requires this same criteria as well as a few other criteria. In order for a function to be considered differentiable, it must contain all of the following: no discontinuities, meaning no jumps in the graph. It must contain no vertical tangents or asymptotes, no corners and no cusps, and both corners and cusps are a type of sharp point that some functions may have. If a function is differentiable, it is also continuous. However, the converse is not always true. Just because a function is continuous does not mean that it is also differentiable. Well, what does this mean? Because for some, this might seem really confusing. Let's actually look at an example. We have this function, y equals the absolute value of x plus 2, graphed in the coordinate plane here. If you notice, we are asked to find the derivative. If we are asked to find the derivative or slope at x equals 0, there is a sharp corner or point here. And the slope quickly changes from -1 to +1 as you move closer and closer to 0 on both sides. Therefore, this function is not differentiable at x equals 0. Another way to look at this would be to try to draw tangents at the line x equals 0. And if I was to actually try to draw different tangents, and I'll do them in a different color so that they're not the same as our function. I could try doing, here's one tangent, here's another tangent, here's another tangent. Notice there are multiple tangents that can be drawn at this sharp point. Therefore, not one single tangent line can be balanced at x equals 0. Therefore, it is not differentiable at this point. So at these cusps, at these points in certain special functions, they're not differentiable at those points because you can draw infinitely many tangent lines at those x values. So a function fails to be differentiable if it contains a corner, a cusp, a vertical tangent, which would be this, or it's discontinuous. There's a big jump from one piece to another. So these are all ways in which a function fails to be differentiable. This is the visual aspect explaining that list from before. There are a couple of different types of discontinuities that are possible for functions. The first one is removable. Those usually happen in rational functions when the same factor occurs in both the numerator and denominator. Another removable discontinuity looks like this. It has a hole in the graph, but then the function is defined at another random point. Another discontinuity is a big jump. Usually occurs with piecewise functions or with step functions. When you have infinite discontinuities, when you have that vertical asymptote and the function increases towards positive infinity or decreases towards negative infinity at those asymptotes, that's an example of an infinite discontinuity. And the last type of discontinuity is what's known as essential. And it happens with certain trigonometric functions as they keep going up and down, up and down, up and down, the closer and closer you get to 0. So that's an essential discontinuity, and those are not differentiable. This Venn diagram explains continuity versus differentiability visually. So what it's saying is that if f of x is continuous at x equals a, then the function value at a exists, the limit as x approaches a of f of x exists, and the function value at a is equal to this limit as x approaches a of f of x. This makes it continuous, and a function is differentiable at x equals a if it's continuous and it has no sharp points or vertical tangents.